Welcome to BAS 121. We're going to go through Chapter 9, a little overview. There are detailed videos on an example of each problem in the book. But we're going to talk about regression analysis. Some of our topics are we're going to talk about the fundamentals of regression, what it is. Then we're going to walk you through some simple linear regressions. Then we're going to talk about whether the regression equation we have fits the data via some analysis of the residuals. And we'll explain to you what a residual is and all of that. Then we're going to talk about, well, what if we want to do multiple regressions, not just a single regression? And then finally, what about if we have categorical data? Remember, two major types of data. There's numeric data and then there's categorical data. So let's just sort of talk about define what it is. So a regression is basically a relationship between two variables, right? So oftentimes we're able, here we have a scatter plot of different x and y values, if you remember algebra. And sometimes, and at least in this data, there looks to be a relationship. As this goes up, as my x value increases, my y value increases. There appears to be a relationship, and this red line is a linear line or model. It attempts to explain this relationship. So my input variable is often our x variable, sometimes called the independent variable or the exploratory variable, or I like to say if you tell me this variable, we can predict what this output variable is, or our y variable, often called a dependent variable, sometimes called the response variable. For example, it's easier to see some examples. If we knew the square footage of a house, because the larger the house, it tends to be more expensive. If we knew the square footage of a house, we could use that data to predict the price of the house or the value of the house, because there's some sort of relationship between how big a house is and the price of a house. Now, intuitively, we all know that's not going to explain all of it, because not every big house is more expensive, but we'll explore that over the course of this video. Now, another thing about regression is when we take this data and we try to fit a line to the data to predict it, that's called the line of best fit. Now, Excel will always give us a line of best fit. It may be good, it may not be good. Sometimes we have data that's very, very scattered, and we can come up with a relationship or try to force a relationship, a linear relationship. But it may be a good fit, it may not be a good fit. So we're going to have to test or do some analysis to see if we've got a good fit or don't have a good fit. Now, the other thing I want to point out is sometimes linear regression is not the best fit of the data. Sometimes we have exponential equations that better fit the data. Sometimes we have logarithmic equations that better fit the data. And sometimes we don't have a good relationship to fit the data. So all of these different things we will be testing for in terms of when is my data exponential, when is it linear, when do we have a good fit, when don't we have a good fit. So that's a little background on what regression is. It's basically trying to explain how one variable is driven by another variable or is related to that variable. So let's talk about a simple regression, linear regression. So let's go back to our house. I think this is a pretty good assumption. House square footage is related to the price of the house. So we could go gather some data, which is actually one of the samples in the book that we'll go through. But here we just put it on a very simple scatter plot. We took our data and scatter plotted it, and we said square footage here, and we said home price here. And we asked Excel to give us the best fitting linear equation, and it gave it to us, and it told us that y, or our home prices, is equal to 35.036 times x, which is our square footage, plus 32,673. Now it gave us this interesting little thing here too called an r squared, which we'll get into, is just says, well, how good a fit do we have? Anytime you ask Excel to fit a line, Excel is going to give you the best fitting line. It doesn't mean the best fitting line is a good fit. So for now, the closer to 1 this r squared is, the better the relationship. The closer to 0, the worse the relationship. This 0.53, the simplest way to think of it is 53% of our variation, or 0.53 of our variation, is explained by square footage. The rest of the variation is explained by something else. We don't know. It could be age of the house, could be the neighborhood, could be a whole host of reasons. But we took our raw data, we put in square footage, home prices, we plotted it, we asked Excel to give us a trend line, which the examples give you exactly how to do that. It gave us this equation, and it gave us this r squared that says 53% of the variation is explained by square footage. So let's move on. So we could simply, if we wanted to calculate it, we could very easily use, now that we have an equation, we could, if we assume 1,000 square foot house, it's as simple as plugging and chugging. We plug the 1,000 in for square footage, and we get an estimate of 67,673. Now, that estimate is going to most likely not going to match the actual selling price of the house. So keep that in mind, that this is just an estimate. It may be it may be relatively good, but it's not going to be perfect. So the next question we got to ask is, well, how much fluctuation does this variable explain, and is it a good fit? So now we get into, now that we have an equation, now we get into the whole subject of, well, do we have a good equation? Do we have a good function? How are we going to determine that? Well, the way we're going to determine that is we're going to take our model, which we have right here, and let's think about a couple of things. All right, certainly we said any one of these individual houses, all of the actual home prices will not be exactly what our model predicts, right? Just like we said, this the model won't be perfect. Now, there'll be a distance between what the actual price of the house is and what we predicted for any difference. This is what's called the residual. Think of it as a difference. The difference between what the actual price is and what we predicted. Now, let's think for a minute. The smaller those residuals, or the smaller the difference between what we predicted and what actually happened, the better our model. So we can actually do some analysis here on how good a model we have by doing an analysis of the residuals. The smaller the residuals, the better our model. The larger the residual, obviously the worse our model. Makes common sense. It gives us, now luckily, Excel does all that math for us, calculates all the residual differences and come up with what's called an r squared, which roughly means, as I said earlier, that 53% of the variance is explained by our variable. Obviously, if it was 1 or 100% of the variance was explained by the variable, that would be a perfect correlation. If 0% of the variation is explained by our variable, that would be a horrible model. So the closer to 1, the better we are. Now, the way it does this is it takes each one of these residuals, and again it squares them, because remember, we go back to remember when we did standard deviation, obviously if we compared the residuals to the added up the residuals, they would add to 0, right? Because the negatives would offset the positives. So we square them, and what's come up with is what's called a least square regression, which is what minimizes the residuals. So Excel goes in and tests all sorts of lines and says, which one of these lines minimizes my residual? And it gives me that equation right there, and it tells me what the r squared is. So that's how Excel kind of did it. Now, there's another tool in Excel that I show you in all the examples, which gives you the you go to data and you go to regression analysis, and it gives you a whole summary, just like the standardized statistics, a whole summary of information. So I'm going to go through now what that information is so you understand it. The great news is Excel does all the calculations for you, or any software, statistical software package will give it to you. But you need to understand what these are. So I've given to you multiple R is just the square of R, and of course R is a square root. R is sometimes called the coefficient of determinant. That's the main point of this thing. That's what you're looking for. Just so you know, adjusted R is used when we're doing multiple regressions. Standard error is simply our sample estimated standard deviation. And the observations is the number in our sample size. But the main thing you're going to want to look for in this summary output, the main thing you're going to use is this R squared. Now, it also gives you an ANOVA section. Now, frankly, this isn't going to be used a whole lot, but I thought it's a good chance to walk you through since it gives us a little reminder of what ANOVA is, and it's a little bit interesting of what's going on here if you think about it. So the purpose of ANOVA is determined how much of the variance is explained by our variable, which is called regression, which remember is the variance between groups. So if we have a lot of variance, if a lot of our variance is explained by the differences between the two groups, then we can say they're related to each other. If a lot of the variance is caused by the residual or the error, then there isn't a strong correlation between the two. So what we're looking in the significant F, now sum of squares and mean squares, and F is an F test, but unfortunately the F test isn't worth a whole lot for us without the test statistic for F. But the significant F basically gives us the p-value. And remember what a p-value is. That's the probability of this event happening just by chance. So what's happening here with the ANOVA is what we're basically doing is we're saying the null hypothesis is that square footage has no relationship or no impact on the price of a home. What we're finding here with a p-value or a significant F, and this is probably the only value you really want to pay a lot of attention to on this ANOVA, this is saying that the probability that we would get such a strong relationship between these two groups, so much of the deviation being explained by the difference between the square footage and the price, the probability that that strong relationship would happen by chance is 3.798 times 10 to the negative 8th power, which is 0.07038. So the probability of that happening is almost zero, which means that we can reject the null hypothesis that there's no statistical relationship between square footage and price of the home. So long story short, what this analysis of variance section is telling us by looking at the significant F is, you know what? The variable we chose to predict our value of our house is related. Now, it doesn't explain all of it. We know it only explains 53% of the variation, but it is a fit to explain it. Now, the reason I say this is kind of not used too much is it's going to be a very, very rare day that you're going to pick something that isn't significant, and understand there's going to be a relationship between this p-value and your r squared. You can't get a good r squared if you've got a very, very low p-value, which, as I said right here, if you have a strong r squared, then you must have a very low p-value or significant F on the ANOVA. That's why the ANOVA section you can glance at and move on. The main thing you're looking for is a strong r squared. But I wanted you to understand what that information was, and the fact that they should be related. If you've got a r squared up over 0.5, then you've almost certainly have a p-value that's very, very long, unless you might have a very strange situation where you have a very, very small sample size. Let's understand the rest of it. The next section that they give you within the regression analysis is the coefficient section. Now this is important. This gives you the coefficients. So there's our y-intercept, 32,673. There's our square footage, 35.02. And notice this is the exact same thing that we got right here. Same numbers. It also gives you the p-value. Notice, remember what a p-value is. It allows us to reject the null hypothesis that there's no relationship between square footage and home prices. Reminder what a p-value is. P-value is the event, probability of the event happening just by chance. So the probability that we would get this strong relationship between square footage and value of the house is almost zero. And notice this p-value is the exact same number as our significant f. Now, there's our p-value. This last section is our confidence interval between, so oftentimes if somebody said to you, if you walked into a real estate agent and said, I'm looking for a 1,400 square foot house, how much does that cost in our neighborhood? And if the real estate agent said, it costs $102,643, we've modeled it, I think most of us would look at them like they're a little crazy. I think what the better response oftentimes is, for a 1,400 square foot house, it's the range, I'm 95% confident. Most folks wouldn't talk that way. Most folks would say, it's going to cost you between $90,000 and $130,000, depending upon, various other factors. There's an example and another video that walks you through how to take this confidence interval and convert it into a range. So that allows you to talk about a range of prices. Let's talk a little bit about residual analysis. How do we know if we have a good fit or assumption? So there are a couple checks we need to make sure the r squared tells us that a lot of it explained, but we also need to do some checks of assumptions to make sure that our model really is a good fit. First thing is to check for linearity. So what we're looking for here is what we've plotted here, and again Excel gives this to you, is the residual plot. So here's all my residuals plotted from 0 to whatever the biggest residual is and across my square footage. The thing I'm looking for is randomness or no patterns above or below. So if you think about it, if I'm a weather forecaster, I don't want a weather forecaster who always predicts, who might be close, but is always off on one high or low, is always off one way or the other, right? You want that error to be random. You want it to be, one day I'm 2 degrees too high, the next day I'm 2 degrees too low. You might be able to find a better model if every single time you do it, you're 2 degrees too low. So what we're looking for in here is we're looking at this and we're saying, does this pattern around 0, residual, does it look random? And it looks very random. That's why I gave the check mark. Now you notice we've got one data point that's an outlier here. It also highlights that. So we may want to check into what this outlier is. So what this outlier means is it's about a 1,600 square foot house that is very highly priced. So maybe there's something going on here. Maybe there's a swimming pool that comes with that house. Maybe there's who knows what. But we may want to check that data. But this, for our sample data, would pass our linearity assumption. The next thing we'd want to check is what's called normality of errors. In theory, we'd like all our errors to be normally distributed around the mean. So again, we'll show you how to do this. We just took the standardized residuals, which takes our residuals and puts them basically in a z-score or standardized score from, and notice I just made a simple histogram, which the other videos show you how to do, from -3 to 3 and more. And notice what we're looking for is we're looking for a standardized bell-shaped curve. And even though this isn't perfect, I would say it's pretty darn close. We have a little bit of skewness to the right, but it's not dramatic. And notice, once again, this more is what? That's our one outlier, right? That shows up there. So this passes the normality of error test. Now, how did I get that? I went to our residual output, which again, there's videos for, which tells you the standardized, and I just did a histogram on our standardized residuals. Next thing we're looking for is to make sure the variations are constants for various values of x. So as I go along this, and this often happens with time series, as I go along here, I don't want all of a sudden, as I get out to one range, of all of a sudden all of them to appear above or below the line, because that might indicate that I'm losing my randomness as I get to certain values of x, as I get out to certain ranges, which might imply that my model is only good for certain ranges. So you want this randomness to continue throughout all values of your x, all ranges of your x. And this one seems to pass this test too. The last test is the independence of errors. You want all your errors to not be independent of each other and to be independent of the variable. So those are 4 tests. The main summary of this is you're just checking primarily your residual plots and your standards of residuals, and you're checking for any patterns and any abnormalities. You're basically looking to make sure that your residuals are random, there's no pattern, there's no patterns as you get out to certain time series to ensure that you have the best model possible. All right, we've talked about simple regressions. What about multiple regressions? So let's go, what is a multiple regression? Well, that's where we might want more than one variable to predict. So let's go back to our home prices. We said it was a function of square footage, and we said that explained 53% of the variance. What if we added more data and we said it's a function of the square footage, it's a function of the neighborhood it's in, and it's a function of the age of the house? If we added in 3 variables to predict home values, we might see our R² significantly increase, which would mean we would have a better model, which would make intuitive sense. And we might be able to, with these 3 multiple regression variables, we might be able to explain 85% of the variance as opposed to just 53% of the variance. So that's, everything else works the same way, except all you're doing with multiple regression is rather than just saying one variable predicts home prices, you might say there are 3 or 4 variables that predict home prices. Last thing we want to talk about in this chapter is what about categorical data? Now remember what categorical data is. That's where, that's like, did they graduate from college or didn't they graduate from college? It's not a number, it's a yes, no. Are they college graduates or aren't they college graduates? Well, if we think about this for a second, that might come in very handy if what we're trying to do is predict income levels. Whether you graduated from college might be a good predictor of whether you have high income. So, but what are we going to do with it? It's categorical data. It's yes or no. You either graduated or you didn't graduate. Well, what we do is we kind of trick it. We assign a number to it. So if you graduated from college, it's a 1. If you didn't graduate from college, it's a 2. And then there's a whole series of solved examples in the rest of the video playlist. So this chapter we covered regression fundamentals. We talked about some simple linear regressions. We talked about how to test for goodness of fit by doing some analysis of our residuals. We talked about what if we want to do multiple regressions. And then we talked about what do we do with categorical data. Hope this helps. Any questions? Send me an email.